Okay, so the next topic is complements of sets. Actually, it is nothing new. It's in fact a special case of the operation of difference of two sets. So let us motivate the notion with an example. Let's consider these two sets U and A. U is the set of all prime numbers, written like this in set builder notation. It is the set of all x such that x is a prime number. And A is the set of all x such that x is a prime number which does not divide 42. In other words, A is the set of those prime numbers which are not prime divisors of 42. There is a chance of confusing the set A as the set of prime divisors of 42. No, it is precisely not that. If one factorizes 42, one gets these numbers which are prime. Okay. And to express the fact that none of these primes is an element of A, we can write these things. All of them are prime. For example, 2 is a prime, so 2 belongs to U. But 2 does not belong to A because 2 is a prime divisor of 42. Similarly, 3 belongs to U, but 3 does not belong to A. And 7 belongs to U, but 7 does not belong to A. And that is why if one forms the difference A, U difference A, then one gets the set 2, 3, 7. That's because U difference A will again consist of primes, but will consist of precisely those primes that divide 42. That's because the ones which do not divide 42 form the set A. And this difference has a name. It's called the complement of A in U. Okay, so that's the complement of a set in a larger set. So let us now see the general definition. The general definition goes like this. Let U be a universal set and A be a subset of U. This U and this A are not the previous sets in that example, okay? These are general sets. The difference set U difference A is called the complement of A in U, the complement of the smaller set in the larger set. We denote it by writing A prime. That is, A prime is equal to U difference A. So it is the set of all elements X such that X belongs to U and X does not belong to A. Okay, so that is the general definition of the complement of a set in a larger set. Now some remarks about this definition. The first thing is that a universal set. Let me again stress the fact that you should not write the universal set. There is nothing like a unique universal set which is so large that it contains every possible object as its elements and every possible set as its subset. Okay, such a set is impossible to exist because of reasons that I cannot discuss right now. We don't need also. Just take it for granted for now that there is no unique largest set that can be taken as the universal set. That's why we do not use the definite article the. We use the indefinite article a. In a given discussion, if a set is large enough so that the objects of interest are elements in that set and the sets of interest are all subsets of that set, then maybe in only that discussion you can use the article the. Let this be the universal set, but then with the understanding that it's actually a universal set in that discussion. That's why the. Okay, so that is one thing. And the second thing is that this universal set itself. See, actually, in order to define the complement of a set A in another set U, just A has to be a subset of U. You may or may not view U as a universal set. In this text, it has been decided to view U as a universal set, but in fact, you can define the complement of A in any set B. Now, if you just simply say B difference A without saying anything else, this just means that B and A are any sets. But in that case, we won't say that this is the complement of A in B. The extra condition that should be there is that A is a subset of B. A must be sitting inside B as a subset. In that case only, this difference is called the complement of A in B. Okay, and it is denoted by A prime. Now, this is not the only notation. There are other notations to denote complements. Another notation is A superscript C. This is, however, an old notation. The popular one and the one that almost everyone uses is this A prime. Okay, so we also use this. And next comes the Venn diagram of this thing, complement. So U as usual is represented by the rectangular region that you can see here, and A also is represented by the region bounded by this simple closed curve. So that means A prime will be the set of those elements in U which are not in A. That means the region in U which lies outside of this region, which is indicated by those parallel lines, those stripes. Now, it may look a little confusing as to which one is A here and which one is A prime, although we do understand, but there are ways of getting rid of this confusion. And one simple way is to just draw some boxes. The white box represents this region. Because we cannot use colors on board, I mean we can use, but we can also show these things like this without using colors. So the white box represents this region and the box with stripes represents that region. So this is A and this is A prime. Okay, so this is another way of showing the Venn diagram. If it becomes confusing as to which one is representing which one, then you can use boxes like this. Alright, so let us next see some more examples illustrating this notion. So this next example has this U. U is the set of all positive integers less than or equal to 10, and A is the set of all odd positive integers in U. Then A prime, that is the complement of A in U, will be the set of those elements in U which are not in A. That means those elements in U which are not odd positive integers, so the even positive integers. 2, 4, 6, 8 and 10. Now a curious observation here is that if you take the complement of the complement, see, first thing, you can take the complement of the complement. Why? Because just like A prime is also after all a subset of U. In order to have the complement of a set in some set, that given set has to be a subset of that larger set. That's the condition. So here A prime is a subset of U, and A prime consists of all the even positive integers less than or equal to 10. So its complement will consist of all the odd positive integers less than or equal to 10. Of course, it cannot be equal to 10, and that is nothing but A. And this is no accident, because this happens in general also. You take any set U and any subset A, the complement of A is the set A itself. In fact, it has a name also. It's called the law of double complement. Let us next see another one. In this one, let U be the set of all students in class 11 of some co-education school. So both boys and girls are there. Let me write like this. It's the set of all elements X such that X is a student of class 11 of a co-education school, and A is the set of all girls A is the set of all elements X such that X belongs to U. That means X is a student of class 11 in that school, and X is a girl. Then A complement, which is U difference A, is the set of all X such that again X is a student of class 11 in that school, that is X belongs to U, and X is a boy. Well, there is something to be said about this example. The example actually has assumed that every student in the school is either a boy or girl, leaving out transgenders. Now, I am not exactly sure if a co-education school allows transgenders or not, but that is the assumption, because otherwise you would have to write that X is an element in U and X is either a boy or a transgender person. But anyway, it is what it is. So let's see another example. In this example, let U be the set of all positive integers less than or equal to 6, and A be the set consisting of the numbers 2 and 3, and there is another set this time. B is the set consisting of 3, 4 and 5. So let us do one thing first. Let's calculate the complements of both A and B in U. We have A complement equal to U difference A. That means from U, you have to remove 2 and 3, and you will be left with 1, 4, 5 and 6. And B complement. From U, if you remove 3, 4 and 5, you are left with 1, 2 and 6. Alright. Now let us take the intersection of A complement and B complement. So, A complement intersection B complement. So what are the common elements? Out of all these elements, 1 is common and 6 is common. Nothing else is common to A complement and B complement. So the intersection is this. You may say, okay, one can find this, what's the big deal? However, now we are going to find another set. Note that we are first of all going to calculate A union B. We are getting to something. Okay, we are not doing things arbitrarily here. So A union B consists of all the elements of A and all the elements of B, and of course if there is anything common, it has to be considered only once. For example, 3 is common. So 2, 3, 4, 5. Now, if one calculates the complement of A union B, hence A union B complement, then from U, you have to remove those elements 2, 3, 4 and 5. So, you will be left with 1 and 6. And it turns out that this is exactly that set. This shows that A complement intersection B complement equal to A union B complement. At least in this example. But surprisingly, this is actually true in general for any sets A and B. Subsets of some universal set, of course, that is always there. This is true in general. Another such law which is also true in general is this: A complement union B complement equal to A intersection B complement. Okay, so taking complement of a union turns it into an intersection. If you take complements of the individual sets, similarly taking the complement of some intersection is the same as the union of the complements of the individual sets. And these laws were first found by the English mathematician and logician Augustus De Morgan. So it's named after him. These are called the De Morgan laws. Actually, strictly speaking, the De Morgan laws are some statements from mathematical logic. And these set theoretic identities are consequences of that statement. But here also, these have retained the same name, De Morgan's laws. So, they were found by these are called De Morgan's laws, named after the English mathematician and logician Augustus De Morgan. And it's customary when you mention someone's name, no? You try to find the time period in which they lived. There is no need to memorize these things, but at least to pay respect to them, to their work, we should remember them like this. Also, make sure that you get the numbers correct, because making a mistake here is really a sign of extreme disrespect. Augustus De Morgan, in fact, was the man who coined the term mathematical induction. He gave the name mathematical induction to that method which nowadays we use to prove statements about positive integers or natural numbers. Okay. So now what I am going to do, although it's not in the text, let us prove the De Morgan laws. Because we mention laws like this and we just simply go without proving them, that's a really bad thing. So let me just prove this in a way in which we proved, I think, associativity of, no, not associativity, but the two distributive laws involving union and intersection. Yeah, that one we did. So just like that, we are going to prove the De Morgan laws, both of them. So let us first prove. Let me write like this. Let U be a universal set having subsets A and B. Then, perhaps I should have given the numbers here. Then number 1, A union B complement. Complement is in U, that is understood, is equal to A complement intersection B complement. And number 2, A intersection B complement is equal to A complement union B complement. Let's do number 1 first. We have so what shall we do, right? Again, recall what we have to do when we need to show that two sets are equal. We need to show that each one is a subset of the other. And this we do by taking general elements. So we have, straight away we start writing like this. X belong to A union B complement. This means X is any element in A union B complement. This implies, now what is the meaning of this statement? By the definition of complements, this means that X belongs to U and, do not mess this logical connectives up, okay, this is and, X does not belong to A union B, okay. Now this implies X belongs to U and what can you write in place of that? X is not in the union of A and B, which means that X is neither in A nor in B, because if it is in any one of them, it will belong to A union B. So that's why X does not belong to A and X does not belong to B. Do you see that in spite of having union, we are having and here? So if someone blindly memorizes that we have to write or when there is union, there will be a mistake. That's because that is the case when you have belongs to, but this is not belongs to. Besides writing full names of mathematicians and showing their time period, you also have to learn how to pronounce their names properly. Okay. Oh, why am I carrying this? Okay, so let's continue our argument. So this means that X belongs to U and X does not belong to A. And because everything is and, no, so this and this are all simultaneously true because all we have are ands. So it does not hurt to again write X belongs to U and X does not belong to B. Now what does this mean? It means that X belongs to U difference A, and this means X belongs to U difference B. I could have skipped this step, but that may be confusing. U difference A means A complement, and this means B complement. So X belongs to A complement and X belongs to B complement, and that is why X belongs to the intersection of them. So any element X you choose here, after all, has to be an element here. Hence, A union B complement is a subset of A complement intersection B complement. Okay, so we have got one of the containments. Let us now prove the reverse containment. Also, you can again write X or you can write Y, whatever name you want to give to the general element, it does not matter. So let me just write X itself, because these are variables, okay? These are dummy variables. You give them any name, after all they are going to represent the same thing. So this time, let X be any element in this. So you can understand that roughly we have to run this argument backwards, as if we have started here. In fact, we have started here and we have to go back. Let's see how far we can go back. So the first few steps are going to be very easy. For example, this just means that X belongs to A complement and X belongs to B complement. If you want, you can write this also after this, but I choose to not write because now we have really understood what these things are. So let me straight away write X belonging to A complement means that X belongs to U and X does not belong to A. This is this, and that other statement means this. Oh, sorry. No, I'm correct. See, I also got confused. Now, this can be written more simply like this. X belongs to U. X is always in U. And X is not in A. And X is not in B. That means X is in neither A nor B. And note that in writing these steps, there is no confusion. We are not confused about why a given step is true. It's absolutely clear that we can in fact write like this. Now, since X belongs to neither A nor B, X cannot be in their union. and that's why X belongs to the complement of the union. Hence, A complement intersection B complement is also a subset of A union B complement. Combining these two inclusions or two containments from the definition of equality, we get our one of the De Morgan laws. Now for the second De Morgan law, I will do only half the job and leave the other half to you. The second one is this. Let me write the identity. A intersection B complement is equal to A complement union B complement. Let me show that this is a subset of this. You will have to show that this is a subset of this as well. Again, we have, so we start by considering any element here. So this means X belongs to U and X does not belong to A intersection B. Now you have to be careful here. The situation here and the situation there are drastically different. Not being in union and not being in intersection mean two entirely different things. Okay, and it is in this kind of situations that you have to take the help of Venn diagrams. That is the primary purpose of Venn diagrams. Say this is your A, this is your B, and U of course is there. So this statement, it says what? That X is an element which is not in the intersection. That means X is restricted to lie in that region, but X can lie elsewhere. X may be here, X may be here, X may lie here also. X may actually lie in A, provided at the same time it's not in B, because otherwise it will belong to the intersection. Similarly, X may lie in B, not lying in A, or X may lie outside of both A and B. So what can we write in place of this? We can write this. X does not belong to A, or X does not belong to B. X has to not be in either A or B. It cannot simultaneously be in both. Again, recall that because OR is inclusive OR, this also means that, what does this OR statement mean? It means that X is either not in A, that means X lies outside of A, under which these two cases come, or X is not in B, that means X can be here or here, or X is in neither A nor B, because OR is inclusive part, and that takes care of these other cases. That's why you can write like this. Okay. Now, because you have OR, either this is true or this is true. If this is true, then you have X in U and X not in A. Or if this is true, that's why we write OR, then X is in U and X is not in B. Now this implies X belongs to, you can write U difference A, but I am going to write at once A complement. Or, do not forget that this is OR, okay? This OR is crucial. This means X belongs to B complement. And this now means X belongs to A complement union B complement, because it is either in A complement or B complement or both. Hence, so we took any element in this set and we have proved that it's also in this set. So A intersection B complement is a subset of A complement union B complement. The reverse inclusion is left to you, and so you are urged to complete the proof of the second De Morgan law. There is strictly no first, no second. One of them is this. All right. Now, besides this, there are some one or two other laws involving complement. So let's mention them also. They are not as involved as the De Morgan laws, but they are not going to be proved. In fact, none of the laws has been proved in the text in this manner. It's not really needed from an exam point of view, but who cares for exams? We are here to learn the things. Some properties of complements. Okay. Number 1. You can in fact start by writing just like how we started writing the De Morgan laws. Let U be a universal set having subsets A and B. I am not writing those things, okay. So the first property is the law of complements. These names in fact are not anything standard. De Morgan's laws are called De Morgan's laws, but the other laws do not have any definite name. In fact, what is written here? Complement laws or the laws of complements, same thing. So what this one says is that if you take the union of a set and its complement, then you get the entire universal set. And the second one says that a set and its complement are disjoint. Their intersection is empty. Number 2, of course, the De Morgan laws. Because we have already written what the laws are, I'm not going to write them again here. Okay, so you know that number 2 has the De Morgan laws. Besides this, there is that other thing which we have observed in the very first example, the law of double complements, double complement. double complementation actually. If you view taking complement as an operation, so this is number 3. Unfortunately, the best kind of study happens when you want to study something, when you want to know something, and there is no exam. You do not have to write any examination. Then you learn the best. This one says that the complement of a set is the set itself. And there is another one. The laws of the empty set and universal set. And this last one says that if you take the complement of the universal set, the universal set in a given discussion, again, I am stressing this again and again because keep in mind, unlike the empty set which is unique, there is no unique largest universal set. If you take the complement of the universal set in itself, the complement of U in U, then you get the empty set. And if you take the complement of the empty set in U, then you get U. So these are the things in this section. And after this, we of course have the exercise set, and we will solve the exercises as usual in the community section. So there is only one more section left, and after that set theory will be over. But anyway, that's just it for tonight. So see you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.